Okay, thank you. So I will first finish the second lecture, which is in certain sense the key, because I didn't really explain till now what was the link between what I explained during the first lecture and the construction in the second. So if you remember yesterday, so I recalled Wick's 1950 paper, the constructions, in particular the two theorems he states to encode so the organization of creation and annihilation operators when you put the annihilation operators to the right, so Wick product or normal order product. I also gave an introduce of algebras and explained that if we have a unital linear form of algebra, then we can construct an automorphism of H. And we can use this automorphism of H to construct a new of algebra structure. Which is isomorphic to the first one by the inverse of phi lambda. Okay, and then I gave an application to show the ubiquity of this, what I would like to call Wick calculus, and the application was to standard renormalization. And I gave the example of multiplicative renormalization. And I mentioned, but maybe I should have stated this, it's different, it's more general than the Rotha-Baxter approach. It includes, but there is more than the Rotha-Baxter approach of Conan-Kreimer. Which is based on minimal subtraction and dimensional regularization. So that which implies that you can have the Birkhoff decomposition. So this is something that was mentioned also yesterday afternoon. So now I would like to come back to the first lecture, so to Wick. Wick's Wick calculus, and explain how it is encoded by this construction, these simple constructions of algebra automorphisms. So let us start with an alphabet, and the idea that it is encoding creation and annihilation operators. We consider the polynomial of algebra over X. So it's the usual algebra of polynomials, but the coproduct is defined uniquely if you require the Xi's to be primitive. This construction is the basic one for all the So for all the theory of free quantum fields and random variables, this is a very simple of algebra. But then it can be sophisticated, as we shall see later. And then we have some commutation rules. That come essentially from in the applications to quantum fields from the links between so Wick products and time ordered products. In Wick's notation, we have this kind of identities. And so we want to move from the product on the right to the product on the left. And here I should say that this product, this algebra product is encoding in this construction, the Wick product. So the Wick product is encoded at this level, and we want to move to, to the time-ordered product. So then it's simple. You define gamma t to be the linear form on the algebra of polynomials. That sends the product of xi, xj to the contraction. And you require gamma t to be 0 on all other monomials. If you do so, it's easy to see what you obtain. I mean, okay, at least if you're a bit used to computations with coproducts and coalgebras, it's a straightforward computation. When you apply this to a product, an arbitrary product in the Hopf algebra, I'm choosing the generators, but it applies to all products. Then what you get is the sum over all pairings. One pairings. So you select arbitrarily two elements, you remove them, from the product, and then you multiply by the contraction. It follows directly from the definition of the coproduct. And you can iterate if you compute, for example, the second power, the second convolution power of gamma t, and you apply to x1, xn, what we'll get is the sum over all two pairings. So where you create two pairs. And then you have something in Wick's notation like xi, xj times xk double dot, xl double dot, and so on. So from these computations that are really straightforward to organize if we want to do so, so I won't do it. What you get is that if you define lambda t with a convolution exponential of gamma t, then you recover in algebraic form Wick's theorem 1, which tells you in this Hopf algebraic form that phi indexed by lambda t of x1, xn is the time order product of the xi's. So this is exactly Wick's theorem, but stated in this more abstract form. The point, of course, is that if you do the encoding that way, you can apply the constructions to any Hopf algebra. So Wick's construction from this point of view is generic for plenty of situations, like the one I explained yesterday, the one of multiplicative renormalization. So now, how about Theorem 2? Theorem 2 is slightly more involved because if you remember, it was about computing products of time-ordered normal products. Then, from the Hopf algebraic point of view, if you translate this problem into a problem of proving identities in the Hopf algebra, what you get is that, okay, notations are not perfect, but So if you take two monomials, y1, yn, and z1, zm, the problem amounts to compute this product with the notation I introduced previously. And this is by definition, so pi gamma t of the exponential of minus, no, sorry, phi lambda t, I'm not consistent with the notations, exponential minus lambda t applied to y1, yn, exponential, convolution exponential of minus lambda t applied to z1, zm. And so I won't detail the computation, but then it's simple. What happens here? Doing so, you create all possible pairings, any number of possible pairings between the elements here, but with signs associated to this exponential minus lambda. Here you create all possible pairings between the zi's, also with signs, depending on the number of pairings. Here, applying this operator, you create all possible pairings among the remaining elements. Then it's an easy game to see that because the signs, the terms cancel, and you are left only with pairings between the y's and the z's. So there are no internal pairing remaining between the y's and between the z's, which is exactly actually the way the theorem is stated in Wick already. Okay, so this shows that the formalism encode Wick's paper and the construction of Wick products in QFT. Now, what about probability? Here, the construction is slightly more involved because if you move away from Gaussian variables, there will be more structure than just pairings. But it doesn't really matter because the phenomenon is taken in charge by the Hopf algebra formalism. So here we start from a family of random variables. With momenta at all orders. We consider again the algebra of polynomials over formal variables that we associate to the x's, and we define the moment map from H to R by sending, say, a monomial x1, xi1, xik to the expectation of the product of the corresponding random variables. Then, so exponentials are really a key to the understanding of all these phenomena. If you write mu as the convolution exponential, what you get is what is called the cumulative map, which is a multilinear map essentially, so a map from multilinear map on families of random variables, which when encoded in that way is simply so linear form on H. And so the connection between this construction and The first lecture is that the family is Gaussian, xi1, xin, say centered Gaussian. If and only if only the degree 2 component of the cumulative map can be non-zero. So this characterizes, in fact, a Gaussian family of random variables. And so, so if you apply this observation, what you get immediately, for example, is the famous theorem of Wick in probability, telling you that if you have a product of Gaussian variables, then you can compute the expectation of the product. So in algebraic form, by computing the exponential of the cumulative map, convolution exponential applied to x1, xn, which is the sum over all pairings, all complete pairings. Among the xi's, so something like x1, x5, x2, 8, and so on. So you want all the random variables to be paired using Wick's original notation. So this is the case, of course, where n is even, and this is 0 if n is odd. Because there are no complete pairings if n is odd. Then the second term I want to state, and then I will stop with random variables, is that if we consider now the convolution inverse of mu, of the moment map, and call this W, so this is definition so I consider the convolution inverse of mu. I apply the construction phi. So what I get is the convolution inverse of mu with the identity, convolution with the identity, and this is the Wick map. Of the first lecture. And so usually is written with double dots. I can just mention that if you look at textbook, the classical definition of, or the most classical definition of Wick polynomials is obtained by inverting this formula. So by saying that mu, that the identity is the convolution of mu with W. So if you write the formulas explicitly, what you get is that x1, xn is the sum over all partitions of n. Of the binomial coefficient times expectation of xi1, xik times the Wick product associated to xg1, xgl, which is equivalent to saying that the identity is the convolution of mu with the Wick product map. Okay, I will stop here. One can go slightly further and move a bit away from Wick construction by connecting the operator product with the Wick product, but I won't do it. This requires a slightly different approach, but it can be formulated also in terms of algebras. So if you look at the references I gave during the first lecture, you will also be able to have a description of the link between an associative product and products like the time-ordered product. But then, of course, you cannot get this through an isomorphism because you want to connect two different algebra structures. Okay, so let's move now to the third lecture, which is going to be about central limit theorems. And I will also mention briefly cumulants again. So here the references are in general the work of Michael Sherman, but in particular an article of 86, the central limit theorem for coalgebras. Then also the work of von Waldenfels in general, which is closely related to Sherman. So, okay, there's a paper of 1978 by von Waldenfels, which is called an algebraic central limit theorem. In the anti-commutative case, which was published in Zeitschrift für Wahrscheinlichkeitstheorie und verwandte Gebiete. And so there's also work of Speicher. In particular, what is relevant today is the article, A New Example of Independence. And one noise, which is was published in PTRF in 1990. And then an article we wrote with Kurush actually the first of a series on the application of algebra techniques in free probability. Okay, so as I won't have time to develop everything, you can go to these articles and we will find all the missing details in the lectures. So let's start with classical and quantum central limit theorems. What I would like to show here is the two things, essentially. First, the relevance of algebra calculus, once again, the fact that it's going to be exactly the same of algebra calculus than the one we considered for Wick constructions. And also point out that it's really essentially the same, not only the same framework, but also the same construction, because things like the cumulative maps, for example, are essential to the fine understanding of central limit theorems. So the problem in general in that situation is to study the limit of, in distribution, of sums of independent, identically distributed random variables with some normalization factors, and there are variants of this formula. So it depends a bit on the probabilistic framework you're dealing with. And so the normalization factor, for example, can depend on the kind of entities you're dealing with. And you can also weaken the hypothesis of independence, for example. And if you weaken the hypothesis of independence, then what I'm going to say is not applying directly, but if you want to analyze what's going on, in the end, you end up with the same tools than the ones for the independent case, from the, at least the algebraic or of algebraic point of view. So an example of the situation where this remark applies is a case where you have a kind of statistical physics problem. You have random variables, you associate one random variable to the integers on the real line. So you have a sort of, I don't know, spin system model or something like this. And you assume that there are correlations between the random variables, but correlations that decay with the distance. And so depending on the decay of correlation with the distance, you can try to study central limit theorems. And so the theorems hold, which are a bit more subtle than the classical ones. But so as I said, in the end, the analysis is the same. So, and you can have the same problem if instead of random variables, you look at sums of independent operators, whatever it means, and you look at quantities like the asymptotic value of the expectation of the trace of a sum of independent families of operators, whatever it means. And so the meaning in general depends on the theory and the context. But the same framework is going to apply to all these situations. So first, the classical case. If you start from an algebra of random variables, then there's a constructions allowing to construct independent copies of A, which I think is due to von Waldenfels, which is the following. But maybe this is Schurman, I'm not sure. I will write this delta n for obvious reasons. You send A to the sum of all possible tensor product of copies of the unit, where you insert A somewhere. So you create a bigger algebra of random variables, and so you have n copies of A, and each copy you have a copy of the random variable you start from. So now, what happens if you want to restate the central limit problem in this framework? So then the problem amounts to computing the following quantity. So we write 5 for the expectation map. So we want to compute the expectation of the product of delta n A1, delta n AK. So now I transform the problem in the problem of computing more generally this kind of quantities. It encompasses the formulation of the central limit problem, the classical one. What we get if we compute this this term, we get the sum of all binomial coefficients times the sum over all ordered partitions. Of K. Well, in general, I will use the following notation if I have set S. Then I write a index S for the product of the corresponding AIs. So this is this follows directly from the form of this iterated coproduct, because in the end it's an iterated coproduct in a certain sense. This is a direct consequence of the form of the iterated coproduct I've defined. And so if I can rewrite this this term as the sum of the products n minus 1 n minus I plus 1 of the sum over all unordered partitions. So I'm left with this term. And then if I assume that the AIs are centered, all the terms containing a block with one element are going to disappear. And the leading order term in the sum is going to be the one, so assuming that, assuming that K is odd, the leading order term in the sum is going to be given by the sum over all possible pairings among the AIs. And only this this term is going to survive in the asymptotic limit, in the sense that so for centered random variables, the limit when n goes to infinity of expectation of normalized by the square root of n to the power k of delta n a1 delta n ak is going to be given by the sum of all pairings of products of expectation of the products, so the pairwise product of the corresponding random variables, a pi 1, a pi 2, a pi k over 2. And it's going to be 0 if k is odd. So it's not completely obvious stated that way, but this is really equivalent to the classical central limit theorem because of the characterization of Gaussian variables by the fact that only the second order cumulant survives when you compute the associated cumulants of families of Gaussian random variables. So this is the algebraic form of the central limit theorem. What I would like to say now is, or to introduce, is a new kind of object. And I will do this through the, what is called, or what can be called the free central limit theorems. And then we're going to see a new kind of objects, a new kind of algebraic and of algebraic phenomena enter the scene. But we're going to see also that the general strategy I've tried to develop to account for this phenomena by means of Hopf algebra is still going to be valid up to some adjustment, in the sense that we will have to broaden the Hopf algebraic picture, but still we will be able to account for this phenomena, again with Hopf algebras. So here the key notion is the following. So a non-commutative, what is sometimes called a non-commutative probabilistic space, is in first approximation, or say the generic case of such a notion is given by an associative algebra and a unital linear form. So the point in this situation is that because we are moving from commutative algebras to associative algebras, there are several notions of independence that can be devised to account for the fact that we enter the non-commutative world. So, for example, if you start from the definition of independence for classical random variables and you think of this data as a sort of non-commutative generalization, there's a notion of independence that is natural, which is called tensor independence, which really reflects from the algebraic point of view what happens in the commutative world. But the most important one is probably the notion of free independence. What does it mean? Assume that we have a family of subalgebras of A. Then they are said to be freely independent if and only if the following condition holds. Given A1, AN in, so one of these subalgebras, AI1, AI2, AIN, such that, so first, these non-commutative random variables are centered, and consecutive indices of the algebras are distinct. Then the expectation of the product is 0. So it looks a bit strange if this is the first time you look at this definition, but it really makes sense for plenty of reasons. And so one point is that this hypothesis is enough to compute an arbitrary product, or more exactly, the expectation of arbitrary products when the BIs belong to some AJ. So from this vanishing condition, you can compute all expectations if you know the values of phi on the AIs. So, for example, if you compute phi a square BA, where A square belongs to A1 and B to A2, you will get what you expect, phi to the 3 phi B. But if you move to more complex expressions like AB, expectation of AB, then you get new expressions with respect to what you would get in the standard probability space setting. So normally in standard probability you would find phi of A square B square. You find phi of A to the square, phi of B to the square plus phi A square phi B to the square minus phi A to the square, phi B to the square. The important point for what I'm going to say is that this expression involves more terms than the standard expression in classical probability. So instead of having only two terms of degree 2, you have terms of degree in phi 3 here, and 4 here, which means that in terms of, if you think in terms of partitions of the initial set of variables you start from, you get finer partitions. Here you get A, B, B. So multisets, say, partitions. Here you get A, B, B. Ouais, d'accord. So, and here I should say one thing, the important thing in this example is that if you look at the partition underlying the consideration of this product where A belongs to A1 and B to A2, you see that the corresponding partition is crossing, in the sense that if you will try to draw the partition using this sort of representations, you cannot avoid having crossings between the components representing the blocks. So I don't have time to detail, but this is typical of free probability in the sense that we'll have this phenomenon, so the difference between free probability expansions and classical probability expansions, a difference between the expression is going to appear only when you consider products of random variables living in independent subalgebra of a given algebra, and so when the associated partition is crossing. So this is to justify, and just by waving hands, not giving proofs, the central limit theorem in the free case. Which says the following: assume that you start from a sequence of random variables and you take copies, independent copies of this family. Then what we get is something that looks like the classical central limit theorem up to a variant. So the limit when n goes to infinity of I of, so the product of what I've written previously, delta 1n delta kn, which in that case is simply given by the sum A11 plus A12 plus A1n over the square root of n, and similarly for the other terms. So the limit of this expression is again 0 if n is odd, for the same reason as previously. But now, because of this phenomena that I mentioned but didn't really explain, the fact that crossing partitions and non-crossing partitions behave differently when you are in this assumption that you deal with freely independent subalgebras of an algebra, then what we are going to get here is the sum over all non-crossing pairings between the variables we start from. So non-crossing pairings means that we consider only pairings like this one. Or more general pairings like, for example, but we remove from the classical central limit theorems all terms like the one I've studied. So, so we'll see during the last lecture why this case is interesting, because it cannot be completely analyzed. If you really want to think in terms of Wick products, you cannot analyze it completely through the use of standard Hopf algebra. But still, something is true. And what is true is the coalgebraic form, the existence of a coalgebraic form of the central limit theorems. So something that encompasses these two examples that also account for many versions of central limit theorems. It's due to Sherman. . And it starts from the following data. So a graded connected coalgebra. So this means that C decomposes as a direct sum of components, that the coproduct is mapping Cn to the direct sum of the Ci tensor Cj, where I plus G is equal to N, and connected means that C0 is equal to the ground field. So in that case, the central limit theorem has a particularly simple form. Assume that phi is a unilinear form. On C, then it holds that the limit when n goes to infinity, a capital N goes to infinity, of the nth order convolution power of phi applied to an element of degree n in C, normalized by, as usual, by the square root of capital N to the n, is equal to the convolution exponential of kappa index phi applied to W, where kappa phi is equal to phi on C2, so on the degree 2 component of the coalgebra, and is 0 everywhere else. So if you think in terms of the, the classical versions I stated of the central limit theorem, this is exactly the same statement up to some sophistication. But now the interest of the theorem is that it applies to all coalgebras. In particular, one can show that it also applies to the free case and to other situations where central limit theorems hold. It does not apply completely to all possible central limit theorems, but still it covers many of them. And it's interesting because of its theoretical form. So I don't have much time left. I will just try to explain very briefly why the theorem holds in that form. So here the key idea is the following. Because we have degrees assumption, if you compute the coproduct of order n, so the iterated coproduct mapping C to C tensor n, if you compute the iterated coproduct of order n applied to an element of degree n, okay, maybe I should do this that way to be consistent. So capital N, and I assume that W belongs to Cn. Then if you compute this, and if n is higher than so capital N is bigger than small n, then for degree reasons, you can have only at most small n components which are not scalar in the iterated coproduct, which means that you're going to have an expression of this form. Sum 1, 1. Okay. With the notation I introduced at the beginning, W. Then I will refine this description, W went, and so on, and so on. And to be more precise, here, because I want to study the appearance of scalars, I will introduce the reduced coproduct, which is the coproduct you obtain by subtracting to the standard coproduct what comes from the co-unit assumptions, the fact that there are always terms like 1 tensor W and W tensor 1 appearing when you compute the coproduct of terms of degree higher than 0. And so for this reduced coproduct, I will use the notation, the Swidler notation, but adding a bar to the terms. So this construction removes scalars from iterations of the coproduct. And so if I look at the iterated coproduct of W, I have terms of this form. So I can have at most n terms corresponding to the iterated coproduct of order n. But I would also have terms like corresponding to the iterated coproduct of order n minus 1. And I will also have terms of the form ultimately tensor product of ones with W, the element of the algebra I'm starting from. So if I look at these terms, the structure of these terms, you see that essentially this corresponds exactly to what I did with partitions when studying the classical central limit theorem. And so the same arguments are going to apply. So for example, because I assume that okay, I forgot to say something. Sorry. I have to assume that phi vanishes on C1, the degree 1 component of the coalgebra. So if I further assume that phi vanishes on C1, then terms in this iterated coproduct, when I apply phi, so when I compute phi to the tensor power n applied to delta n of W, all the terms corresponding to iterated coproducts, iterated reduced coproducts of order bigger than n over 2 are going to disappear, and the first obstruction is going to be given exactly by the term that is here. So this is exactly the same analysis than the one I've done for the classical central limit theorem, up to the change of languages. So moving from the algebra of polynomials, where the combinatorics is easy, to the combinatorics of coalgebra, where you have to introduce some extra arguments to account for what's going on. But I will stop on this. What I wanted to show mainly is that central limit theorems obey really essentially the same kind of rules than Wick calculus. All of this forms a unit, and I didn't explain this, but if you want to move to more sophisticated versions of central limit theorems, you will see in the literature things like Hermite polynomials, for example, appearing, or orthogonal polynomials associated to other random variables, or also Wick product associated to arbitrary distribution appearing. So this is one thing, and the other thing I want to insist on is that we have started to see that There are also some phenomena that show up that are a bit different than the usual ones when we move to non-commutative probabilities, when we move from the classical world to the non-commutative world. And if you think in terms of quantum field theory, instead of thinking in terms of probability, this shift is closely related to the idea of moving from free quantum fields to interacting quantum fields. Because also in this setting, changes are going to appear with respect to the standard analysis, or they are a bit different from the ones that appear when moving from commutative to non-commutative probabilities. So we'll stop here.
The central limit theorem you have on slide 4, is that physically justified? Is that a kind of result that you would find useful using in physics, for instance? I see why it's true, but does the form have some sort of practical interpretation?
Practical use, I don't know, because one should look at the applications of non-commutative probabilities to physical systems. I guess you, if you really want to do it, you can probably, and if it's true, then probably it has been done, but I don't know the references. Probably you can apply this to random matrices. Most likely it should hold for the analysis of random matrices. But I have no example in mind, but I guess and what is true is that if you look at random matrices and you look to the asymptotic limit in size, and you look at the same time at central limit theorems, then the analysis boils down to this one of free probability. And then, so this makes a connection. But probably it can be applied also to say, finite dimensional random matrices. But that's a very good question, actually, because if it's true, then we should add this in the picture, because this would be a nice illustration. But it's very generic in the sense that there are plenty of situations where I don't know if it's always possible to express things in co-algebraic terms, but there are many situations where when you're going to the asymptotic limit and you have graphical expansions of quantities, then in the asymptotic limit the sum is over pairings or two-dimensional objects. So it can be characterized by the number of pairings directly, but it can be characterized in terms of genus of surfaces, in terms of, so this is a more generic situation. But if the question is, can you connect this to this construction? I don't know. I'm only sure that the general philosophy is always the same when you have this geometric recursions, whatever it means. The asymptotic analysis relies always on the same kind of combinatorics at the very end. So like the behavior of binomial coefficients and the way you can expand them polynomially and study their growth. So